Okay, as we were saying, elements are defined by their number of protons. All elements are made up of the same subatomic particles in the same relative positions, but remember what distinguishes one element from another is the number of subatomic particles. And the one that's used to define the number, basically used to define which element it is you're dealing with, is the number of protons. And the number of protons is also known as the atomic number of the element. And the atomic number has the symbol Z, capital Z. And each element has a unique number, unique atomic number, and unique number of protons. So each element has a unique number, both for the number of protons and the atomic number, which happen to be the same. And that's basically how the periodic table is arranged. In order of increasing atomic number. If you look at the periodic table, you notice that the atomic number, which is the whole number that's within each square, goes up by 1 for each successive space that you move left to right. And that's because the number of protons in the atoms of an element go up by 1 for each successive element. And the periodic table seems at first glance also to be arranged according to atomic mass. If you look at the masses of the elements, those are the numbers in each square that have decimal spaces in them. They go up from one space to the next for the most part too, but not totally consistently. There are a few spaces where the number for the mass of the average atom of an element actually goes down a little bit from one space to the next. And so it's the atomic number is responsible for the entire organization of the periodic table. Known elements have atomic numbers anywhere from 1 to, I think the latest one is about 118 or something like that. And so that's quite a bit of, quite a few elements, considering that there are only something like 68 elements known when Mendeleev first laid out the periodic table. It's really quite an impressive achievement on his part that his table was able to be so easily adapted to accommodate so many new elements that were not known in his time. It's a tribute to a good theory that it's able to predict and accommodate so much that comes afterwards. Each element also has its own symbol. The symbol for each element would be the letters that are in each square. And those 1 or 2 letters come from the name of the element. And it's most of the symbols are consistent with the name of the element in English. But there are quite a few that come from Latin, and a couple here and there from Greek or German even. And it's important to remember when writing the symbols for elements that the first letter of each symbol is capitalized, and the second one, if there is a second one, is not capitalized. And an interesting example of how not following those rules can lead to confusion would be to look at the metal whose symbol is CO. That's cobalt. It's a relatively unreactive metal that's kind of similar to nickel, versus capital C, capital O, which is carbon monoxide, a poisonous gas. So capital C, capital O is, yeah, poisonous gas. You don't want to confuse the two of those. Also, note that when there is more than one element together in a compound, you just basically write the symbols for the elements one after another. And if there's more than one atom present in each unit of the compound, then you can convey that by putting a little subscript number after the symbol for each element, indicating how many atoms there are in each unit of the compound. If the number of atoms present is just one, you don't actually have to write a number because the symbol itself represents at least one atom of the compound. Okay, so some of the symbols are pretty straightforward, like CO for cobalt, or for that matter C for carbon and O for oxygen. But some of them are not so sensible. Even some of the ones that do make sense in English have to be you have to be careful not to mix them up. Like for instance, C is for carbon and Ca is for calcium, even though it could very easily have gone the other way. For the most part, the elements that have been known the longest have the simplest symbols, like C for carbon, for instance, because that's been known since prehistoric times. Whereas something like calcium is so reactive that it's really only found in compounds in nature, and it wasn't isolated until I think sometime in the 19th century as an element. Anyway, some of the older elements, particularly those that were popular with the alchemists in the Middle Ages, still use symbols from Latin or Greek. And so some of the examples of those, let me see here. I've got a list somewhere of ones that I wanted to mention. Whoops, sorry about that. So let's see, we've got sodium. The symbol for sodium is Na. That's because in Latin it's called natrium. And potassium has the symbol of K because in Latin it's kalium. Iron has a symbol of Fe because in Latin it's ferrum. Tin has a symbol of Sn because in Latin it's stannum. Copper has a symbol Cu, which is almost what you'd expect it to be, but not quite, because in Latin it's close, but not quite the same as cuprum. Lead has the symbol Pb because in Latin it's plumbum. This shouldn't be too bad to remember because the word plumbing is derived from the Latin word for lead because of the tendency over the years to use lead for piping, which is something that's been in the news lately with Flint, Michigan and other cities. So that hopefully won't be too hard to remember. Silver has the symbol Ag because in Latin it's argentum. Gold has the symbol Au because in Latin it's aurum. It's from this word that we get the word aura, A-U-R-A. Somebody has an aura if they have a kind of glow about them, kind of like gold does. And one other place you may have encountered that is if you remember the old James Bond movie Goldfinger, where the villain was obsessed with gold. Remember what his first name was? Auric. Yep, so that's from here. There's also mercury. Now, the word mercury comes almost directly from Latin, so you might think you're on safe ground here, but you're actually not, because this one's from Greek. Hg stands for hydrogyrum. Which actually makes water, which means water making. And it's because mercury was often found in the presence of water in nature. So the ancients, I guess, thought that mercury was actually making the water, even though it wasn't. You don't have to know these Latin names, but you should be familiar with the symbols. So if, you know, knowing the name might help you with the symbol, hopefully. Okay. So remember, each element has its own unique symbol and its own unique atomic number, and the two of them go together. They're kind of mutually reinforcing and really redundant in a way, because, you know, for instance, if you've got carbon, you've got something with atomic number 6. If you've got something with atomic number 6, then you've got carbon. So the symbol and the atomic number, either one of them, can be used to identify an element equally well. Okay, the next thing we need to talk about is isotopes. And just as a quick, you know, this is a quick reminder of what isotopes are. It means different numbers of neutrons. Isotopes, in a more exact definition, are atoms of the same element which means they have the same number of protons and the same atomic number that happen to have different numbers of neutrons. Neutrons are one of the heavier parts of the atom, and so a different number of neutrons means that different isotopes will also have different masses. Oh, sorry. This is one thing that Dalton was wrong about in his atomic theory, where he said that all atoms of the same element would have the same mass. Dalton didn't know about neutrons yet, so he didn't know about isotopes. So yeah, we'll let that one go. Okay, so carbon is atomic number 6. So all carbon atoms have 6 protons, but carbon atoms can actually have 6 or 7 or 8 neutrons. The isotope symbol, for shorthand, you can give the name of the element and the mass. Like, for instance, carbon-12, that's one of the isotopes of carbon. Or carbon-13, that's another one of the isotopes of carbon. Or carbon-14, yep, that's another isotope of carbon. These are the 3 isotopes of carbon. There's also a symbol you can use that takes the form of this. Basically, it's the mass of the isotope used as a subscript, or superscript rather, before the symbol for the element. So carbon-12 would be written as superscript 12 and then the capital C. Carbon-13 and carbon-14 would be done similarly. You can also write in the atomic number in these symbols, but you don't actually have to, since the capital C itself indicates that you're dealing with carbon. So writing in the 6 for the atomic number is kind of redundant, really, because, again, carbon is number 6, atomic number 6 is carbon. So you don't really have to write that in, but I'm going to do it anyway, just to be complete. Okay, so the bottom number is the atomic number. And the top number is known as A. So atomic number, remember, is also the number of protons in an atom. And A is what's known as the mass number, or the mass of that particular isotope. This is not the mass from the periodic table, although in some cases it might be very close to that mass. This is not the same thing. The mass number is actually equal to the number of protons plus the number of neutrons for a specific isotope. So in order to find the mass number, you have to know what isotope you're talking about. Just about every element in the periodic table has at least 2 isotopes, and each of those isotopes will have its own mass number. Remember, the mass that you see in the periodic table is actually just a weighted mass of the masses of all of the isotopes. All right, so those are the symbols. Now that we've discussed neutrons, we can actually have a look at finding the numbers of subatomic particles in a specific atom of a specific element. Remember that the number of protons is the same as the atomic number, or Z. The number of electrons in any given atom is also the atomic number, because atoms are neutral overall. So however many positive charges you have to have the same number of negative charges. The number of neutrons now will be the mass number minus the atomic number. But remember, the mass number is the isotope mass, not the mass from the periodic table. Or in other words, we're talking about, in the symbols that we used up above here, A minus Z. So you can, what this means is that you can only find the number of neutrons. Uh-oh, gets spooky out there. Anyway, you can only find the number of neutrons for a specific isotope. So you can find the protons and electrons for any atom of an element without even knowing what isotope you're talking about. You know, if you're talking about carbon, all carbon atoms have 6 protons because it's atomic number 6. All carbon atoms will also have 6 electrons because atoms are neutral overall. But for the number of neutrons, you need to know which of these 3 isotopes you're talking about, so that you know which mass numbers to subtract the atomic number from. Again, don't use the number in the periodic table, because that is an average of all of the isotopes. And what you need here for mass number is a whole number. Okay, and the whole number would be the number like here, which is the mass of the isotope. So looking at carbon, you can look at the isotopes of carbon, and some things you might want to know about them would be how many protons are there, how many neutrons are there, and how many electrons are there. And of course, one of the isotopes is carbon-12, one of them is carbon-13, and one of them is carbon-14. Okay, so for carbon-12, the number of protons is going to be, in fact, you might want to try and fill this in yourself by pausing the video and then coming back and looking at what we find when we do it together. So I'll give you a moment to pause the video. Okay, and now we're back, hopefully. The number of protons in any atom of carbon is going to be the atomic number of carbon, which is 6. And in fact, I just decided to write it in there anyway. It may, remember, it may be there or it may not be. If the number is there, you can take it directly from the symbol. If the number is not there, then you have to go to the periodic table and find capital C for carbon and see what the atomic number is. So 6 protons. You can jump to electrons because we know it has to have the same number of electrons if it's going to be a neutrally charged atom. And notice there's no charge indicated here, so we can assume that's a neutral atom. Now for neutrons, we have to look at the mass number. Mass number, which is 12, minus the atomic number, which is 6, gives us 6 neutrons for carbon-12. Okay, for carbon-13, it's still carbon, so it's still atomic number 6, so there will be 6 protons. And it's still a neutral atom, so there will be 6 electrons. For the neutrons, well, since it's different numbers of neutrons that causes the mass to change, and the mass has gone up by 1, you might suspect that there'd be maybe 7 neutrons in carbon-13, but let's make it official and find out. Mass number, which is 13 for carbon-13, minus the atomic number, which is still 6, equals, what do you know, 7. Carbon-14, again, still carbon, so it's still atomic number 6, so that's still 6 protons. Still a neutral atom, so there would be an equal number of electrons. And for the neutrons this time, yeah, it's going to be 8, but let's make it official and take the mass number, which is 14, minus the atomic number, which is still 6, and what do you know, it ends up being 8. So carbon atoms all have the same number of protons, all have the same number of electrons, but they have different numbers of neutrons, which is responsible for their different weights. There is what's known as natural abundance for elements, for isotopes of elements. The natural abundance for an isotope is just the percentage of all of the atoms of an element that are made up of a specific isotope. So we could add a line to this table up here for the abundance of these isotopes. It turns out that a lot of the masses, the atomic masses in the periodic table are very close to whole numbers because a common situation is like in the case of carbon, where you have one isotope making up a vast majority of all of the atoms of an element, and the other isotopes making up very small proportions. And that is indeed the case with carbon, which is why the atomic mass, which is the weighted average of the masses of all of the isotopes, for carbon is 12.01. It's almost exactly 12, because 99% approximately of carbon atoms are carbon-12. As a decimal, if you're going to do any math with it, you would render 99% as 0.99. And carbon-13 makes up a little less than 1%, a 0.9% to be exact, well, more exact, of all carbon atoms. As a decimal, that's 0.009. And carbon-14 makes up about 0.1%, or about 1 atom out of 1,000, or 0.001 as a fraction. So that means if you had a pile of carbon and you plucked out a single carbon atom at random and looked at it very carefully, you would discover that there's about a 99% chance that what you plucked out was an atom of carbon-12. There'd be about a 1% chance that you get an atom of carbon-13, and about a 1 chance out of 1,000 that you would get an atom of carbon-14. And that, again, is why the number is so close to 12 for the mass in the periodic table. Okay, now ions. Ions are caused by gain or loss of electrons by an atom. We know that neutral atoms have the same number of protons and electrons. And because they have the same numbers of positive and negative charges, that's why they're electrically neutral overall. But in many reactions, many elements can gain or lose electrons. So it's possible that some elements might gain electrons, and what happens in that case is that the atom will become what's known as a negative ion, because now it has a negative charge. These are also known as anions. And this kind of behavior is typical of the nonmetal elements. Nonmetal elements are the ones in the upper right-hand corner of the periodic table above the sort of zigzag stair-step thing that goes down the right-hand side. The other thing they can do is lose one or more electrons, in which case it becomes a positive ion, which is known as a cation. And this kind of behavior is typical of metals. Metals are the elements in the periodic table that cover the entire left-hand side and the center area, and even parts of the inner lower right-hand side. Turns out a vast majority of chemical elements are metals. There are something like 118 or so chemical elements known, and about 90 of them are metals. So there are a lot of atoms out there that basically want to give up electrons. I'm going to stop there because I see we're just about at a half hour, and I'll start up again, pick up here in the next segment. Okay, so see you in a moment.